Okay, here we go. Again, a review from yesterday. First step, if possible, if there's a plus 1, plus something, minus something, move it over, clean it up. If there's a number being multiplied by this 3 to the x power, move it up, over, clean it up. Get it into its purest form, which is right here. This one's already cleaned up. 3 to the x power equals 29. Once you get it in this form, we're now going to change forms. Because there's really nothing else you can do. You can try to move the 3 over, but again, you've got that x floating in the air. And we have no idea what to do with an x floating in the air. So, to go from 3 to the x equals 29 to your logarithmic form, that'd be log base 3 of your number on the other side is equal to your exponent. And once you've changed forms, pretty much you're done. Because now all you've got to do is take that log base 3 of 29, plug it into your calculator, and it gives you the answer. Remind me, Brad, how do I type that into my calculator though? Log 29 divided by log 3. When you take your ACT, let me remind you about something though. You don't have to have a calculator to take your ACT. If anybody's taking it again, I believe you are. So could you actually plug that into your calculator to get you your answer? No. How does the ACT leave your answer? There. They would leave it probably as log 29 divided by log 3. They wouldn't go that next step and plug it in. But when you do plug it in, I know that 3 to the third power is 27, and 3 to the fourth power is way too big, so I'm going to get about 3 point. Has anybody got typed in? So about 3.07. And you can check yourself by typing in 3 to the 3.07 power, and you should get something really close to 29. Okay, next equation here. Have the natural log of x squared equals the natural log of 3x. Think back to these problems. X over 3 plus 1 over 3 equals 5 over 3. Somebody tell me what x is there. 4. Does that make sense? Does everybody see that, honestly, the 3's, do they even matter? The numbers on the bottom, since they're all the same, they really don't matter. Look at this problem. It's very closely connected with that. The log, or natural log in this case, the natural log of x squared equals the natural log of 3x. Guys, anytime you have a log equal to a log, dump your logs. Dump your logs. And you're going to be left with x squared is equal to 3x. If the log of one thing is equal to the log of another thing, then those things must be the same. It is now quadratic. You solve it just like a quadratic equation. Move the 3x over. You now have x squared minus 3x equals 0. Your next step is to always factor. Now, from here down, it's just old stuff. But hopefully it's a good review of the old stuff. There's no constant term. So you don't say what adds to give me this and multiplies to give me this number over here. You simply say, well, I've got common factor. Pull that common factor out. And you have two different answers. Set them each equal to 0. Either x is 0 or x minus 3 is 0. So now, be careful though. Go back and think about domain. I told you you can't take the log of a negative, and you can't take the log of 0 for this reason. Let's go to a regular common log. If I ask what the log of 0 is, you're saying 10 to what power gives you 0. That's not possible. Okay, you can't raise a number to a power to get 0. You can't raise a number to a power to give you a negative. Like if you had log base 10 of negative 1, 10 to what power is negative 1? It's not possible. It doesn't exist. So therefore, anytime you have the log of 0 or the log of a negative, it is undefined. Plug in 0, either here or here. You get the natural log of 0 equals natural log of 0. You cannot take the natural log of 0. But now plug in 3, you've got the natural log of 9 equals natural log of 9. That checks out. That's okay. So really, this is not a log problem. Okay, this, just get rid of the logs. It's just a basic quadratic problem. We've already worked that type problem, but now this is a little bit easier. 10 to the x power equals 50. There's nothing we can move over. Now, if there was a 5 out front, we would divide by 5 first, but there's not. 10 to the x power equals 50. All we can do is change forms. Let me do that, Avery. Log base. Good. It'd be base 10, so it's just log. That's a common log of equals x. So to do that one, that common log, that log base 10, that's the one on your calculator. So all you got to do to work this problem, hit log 50, enter. And you're going to get x is about 1.7. Sound good. And here's one of those. Use a calculator to find this. Now here, 2e to the 0.5x power equals 6. I can move this 2. This 2 is being multiplied by this whole thing. Go ahead and move that 2 over first. So you have e to the 0.5x equals 3. Because to move that over, you divide by 2. And nothing else can be moved over, so change forms. That'd be log base e, which is your natural log. Log base e of 3 equals 0.5x. If you would like to, go ahead and get x by itself. Since that's being multiplied, go ahead and divide by 0.5. Now, the ACT is going to leave this problem a little bit different. They're going to do this to you. Instead of dividing by 0.5, they're really going to want you to change that to 1/2. Because really, a fraction divided by 1/2, that doesn't look very clean. To divide by fractions, we flip and multiply. So instead of divided by 1/2, they're really going to want you to write that as times 2. So 2 times the natural log of 3. And what I would like for you to do, because we're going to come back to this problem here in just a second, 2 times the natural log of 3 actually could be cleaned up one more step. But in order to do that, we're going to have to talk about your rules of logs, which I think is what we're about to lead right into. However, let's go ahead and get I'm terrible about writing an H instead of natural log. Let's go ahead and type that into our calculator and get a decimal approximation. Although that's not what the ACT is going to ask for. They're going to ask for what I'm about to show you, but 2 times natural log of 3, has anybody got that? You get it, Ivy? 2.2. Sounds good. Oh, it's just 2 times the ln button, 3, enter. That's how you got that. Okay, the other day we talked about bank interest. And just a reminder of the formula that we used, A equals the principal, and then A was the amount of money that's now in the account, was equal to the principal times 1 plus all over n, raised to the nt power, where n was the number of times that was compounded per year, t was how many years that you leave it in there, r is the interest rate, and p is the principal. $8,000 is invested at 9% interest, compounded continuously. Got a problem though. What do we put for n? Now, let me explain something. Continuous compounding. If you put like 100 million for n, honestly, you'd get the same answer. But there's an easier formula to use. Compounding continuously means that the millisecond that is compounded again, just right after that. So, like I said, you could put like 100 million, 100 trillion, whatever. You could just put some huge number for n here, and you're going to get the same answer. But I would much rather use this formula. If interest is compounded continuously, and this one would be compounded annually, semi-annually, quarterly, monthly, daily, hourly, whatever, which hourly would be very close to APERT as well. You can nearly use the same formula there. But anytime you see that continuous compounding, just plug it into this. So $8,000 at 9% interest, compounded continuously, then how long? Different. How long would it take it to grow to 20,000? So they give you the amount of what you want, the amount of money you want it to grow to, They give you the principal, they give you the rate, but you're looking for the time. You're looking for how long would it take. And we didn't have one of those problems before because we didn't know how to solve these equations. Now we can, so let's plug everything in. You want $20,000 out of your investment. The initial investment is $8,000. I'm guessing that's going to take a while. So let's see, 8,000 go to 20. E, that number's already plugged in. E is a number. Don't try to plug in something different for it. There's nothing in that problem that you plug in for E. It's 2.718. Raised to the RT power, which is 0.09 T. That's the equation you're looking to solve. We just solved one identical to it. Step number one, move over anything that's not firmly attached. 8,000 is being multiplied, so we can come over here and divide by 8,000. When you type that into your calculator, don't do 20,000 divided by 8,000. Guys, mark some of those zeros out. Just do 20 divided by 8 so you don't have to plug so much in. Reduce that fraction. Or if you wanted to plug in 10 divided by 4, it's the same thing, and I think you get 2.5, correct? If you can do that in your head, what I just did, you can really impress some people. 20,000 divided by 8,000, and just pretend like you're trying to divide that in your head, and just, instead of dividing it, you're just reducing it. Mark out some zeros. 20 over 8, reduce that to 10 divided by 4, or to 5 divided by 2, and just keep reducing that fraction down, and 5 divided by 2 is easy. 5 divided by 2 is 2.5. It's the same thing. This is 5 divided by 2. So you have 2.5 equals e to the 0.09 t power. There's nothing else that can be moved over. So from that point, you simply change forms. That would be log base e of 2.5 equals 0.09 t. And to get rid of the 0.09, simply divide by it as well. There's what you type into your calculator. The natural log of 2.5 divided by 0.09. Abby, once you get that, can you tell me what you get? I'm guessing several years. 10.9 years. Which honestly is not too bad. What was the interest rate there? Oh, never mind, 9%. You'll never get a 9% interest rate. Sorry. I think the banks, has anybody been to the bank lately? What's your interest rate on loans right now? Like 0.1%? It's not 9%. Okay, 9%. Now, if you invest in something like a CD or something like that, you might get higher interest rates. I still don't think you're going to get 9%. That's a really high yield. Okay, here we go. The 4 logarithm rules. The 4 basic rules of logarithms. You're going to see that these rules are very similar to the rules of exponents, which I remind you, x squared times x to the third is x to the fifth. When you multiply these things, you add exponents. X squared to the third power is x to the sixth power. X to the fifth over x to the second, you subtract exponents, is x to the third. The rules that we're about to do are connected with those. Why are they connected with those rules? Because logarithms are exponents, just simply written in a different way. So you're going to see a lot of similarities between these rules of exponents and the rules of logarithms. The first rule of logarithms is called the product rule. The product rule states this. If you have the log of 2 things being multiplied together, the log of x times y, you can split that log into the log of x plus the log of y. Multiplication can be split into the sum of logs. So something else I could do, I could take the log of 12 and I could split that into the log of 3 plus the log of 4. Now you're going to probably be using this law backwards more often. To add 2 logs, you just work the same problem backwards. If you have the log, and this works for any base, let's do log base 3 of 9 plus log base 3 of 3. This is the same law backwards. Log base 3 of 9 plus log base 3 of 3. To add two logarithms, first off, you have to have the same base. And again, it goes along with x squared times x to the third. To multiply these two things, you add the bases, right? Or excuse me, you add the exponents because they have the same base. It's connected with this rule of logarithms. To add two logarithms together, you multiply. To multiply two exponents, you add. You see the connection. It's the same thing. To add two logarithms together, you're going to multiply the arguments, is what I call them. Now, to prove, log base 3 of 9 is 2. Log base 3 of 3, 3 to what power is 3, is 1. This is 2 plus 1, which is 3. Yeah, that checks out. I wanted to do something concrete that you can actually see the answers to, just to prove to you 2 plus 1 is equal to 3. Log base 3 of 9 plus log base 3 of 3. Multiply the two arguments gives you log base 3 of 27. First problem. Log base 3 of x plus log base 3 of 6. To add two logarithms if they have the same base. Anna Marie, help me with this. That would equal the log base 3 of... She's not here. Thank you very much, Lydia. Log, just to add these two things together, you would have it as an answer log base 3 of 6x. Done. To add two logarithms, simply multiply the arguments. Natural log of 3 plus natural log of x squared plus natural log of y. Now combine all three of those, you now have the natural log of Now why are we going to have to do that? You're cleaning your logs. Okay? Cleaning your logs. So, if you know your product rule, then if you'll think real hard, I bet you know your quotient rule. Okay? Quotient rule says when you have the quotient, you have a log of two things being divided. The log of 3 halves. When you have the log of a quotient, you can split that log into the log of 3 minus the log of 2. Now what rule is that connected to? X to the 5th power divided by x to the 3rd power. You have a quotient. How do you divide those? You subtract your exponents. Okay, it's very closely connected with that rule. So the log of 3 halves is the log of 3 minus log of 2. Natural log, let's do the natural log of 0.5. 0.5 is the same thing as 1/2. You could write that as the natural log of 1 minus the natural log of 2, correct? Which actually leads us right into the law that we're about to do. Does anybody know what the natural log of 1 is? This is e, right? E to what power is 1? We did that one 2 or 3 times yesterday, just because it pops up a lot. E to what power? 0. Anything to the 0 power is 1. So anytime you have the log, natural log, log base 1, log base, well, you can't have log base 1, log base 2, log base 3, log base anything of 1, you're going to get 0. This is 0 minus natural log of 2, which is the negative natural log of 2. So I would need you to go that extra step and clean that up. And the log of any base of 1 will always be 0. So here we go. Here's your quotient rule. Log base 3 of 24 minus log base 3 of 4. We're working it backwards. The log of a quotient can be rewritten as subtraction. So log base 3 of 24 over 4 is log base 3 of 24 minus log base 3 of 4. So we can rewrite this, and we can actually clean that up. 24 over 4 is log base 3 of 6. A lot of people say, oh, I know log base 3 of 6. That's 2. No, it's not. 3 to the 2nd power is 9, not 6. 3 to, let's see, I think that's going to be something like 1.5. Because 3 to the 1st power is 3. 3 to the 2nd power is 9. So 3 to some power between 1 and 2 would give you about 6. Anybody I see some of you plugging that in. What did y'all get when you type in log base 3 of 6? Natural log of x to the 6th minus natural log of x squared. Anytime you have subtraction, rewrite it as the natural log of, help me, Tootin. That's it. And then we clean that up. Clean it up for me, Logan's not here. Daniel, that'd be the natural log of x to the 4th. Which again, there's another rule that we could take this a step further if you know this rule that I'm about to show you. So let's go ahead and go into that rule that I'm about to show you. It's called the power rule. So you have the quotient and the product rule. If two things have been multiplied, you can split it into addition. If two things have been divided, you can split it into subtraction, or you can do it backwards. If you have a log plus a log, that's the log of the product. Log minus a log, that's a log of a quotient. That looks, this just looks confusing to me. Anytime I look at math book stuff, it's just crazy. That means nothing to me. I would rather see this. Here's you an example. If you have the log of something to a power. Now this is kind of wild, why this is true. If you have the log of something to a power, you can take that power and actually move it down front. If you have the log of something to a power, that power can actually be taken from the exponent and moved out in front of that log. So the log of 3 squared is the same thing as 2 times the log of 3. That might come in handy when we're solving equations. And you really don't want x to the 3rd power, you just want plain x. Take the 3, move it out front. That is 3 times log x. That does work backwards as well. You have 2 times, and let's go back to that problem I told you a while ago. It was 2 times the log of 3, wasn't it? When I told you to star. I think it was 2 times log 3. You can clean that up one more step. 2 times log of 3, if a number is being multiplied times a log, you can take it into an exponent. So this number that's out front, the same way you can move it down front up here, you can take a number that's out front and move it up here. So the log of 3 squared actually could be written as log 9. It just looks better. So a number out front can be taken up into an exponent and rewritten. Rewrite each expression in terms of log 3. The 8 in the exponent can be moved out front. That's 8 times log 3. That's all they want you to do. I don't want log of 3 to a power. I want just plain log 3. Well, this is 8 log 3s. 8 times log 3. A little bit tougher here. I have to rewrite this thing. Skylar, before I can even have an exponent, I'm going to have to rewrite it. What can I rewrite the square root of 3 as, Skylar? A square root can be written as a what power? Half power. 3 to the 1/2 power. The number on the bottom is the radical. The number on top is the exponent. That's a 3 to the 1st power. So that the square root of 3 is 3 to the 1/2 power. So 3 to the 1/2, I can take that 1/2 and bring it down front. So that's 1/2 times the log of 3. I want to rewrite this in terms of log 3. I don't want log 1/3, I just want 3. And since we're on the power rule, let me show you, there's 2 different ways we could do this. This is quotient rule, all the way. This is log 1 minus log 3. We all know what log 1 is. We talked about a while ago, log 1 is always 0. This is 0 minus log 3, or just negative log 3. Let me show you another way of working this that fits. This can be written as a negative exponent. Excuse me. We can rewrite 1/3 like this. That's log of 3 to the negative 1 power, is it not? Bring that 3 back to the top. The one really doesn't matter. Bring the 3 back to the top. Since it's 3 to the 1st on bottom, it would be 3 to the negative 1 on top. Now use that rule of log. An exponent can be moved down front. And you get the exact same answer you did the other way. Okay, either direction you take it, you get the same answer. Okay, these are a little bit tougher. These are actually the tougher of the log problems that you're going to see. We want to somehow take the log of 27 and write it not as log 27, but we want log 3s. somehow get rid of the 27, turn it using those 3 rules of exponent, or 3 rules of logs. We'll do your 4th rule here in a second. I want to somehow turn 27 into 3. And first off, you need to know the relationship. How can I turn a 27 into a 3? What's the relationship between 27 and 3? Does anybody know? 27 is the same thing as 3. How? 3 times 3 times 3? 3 times 3 is 9, times 3 is 27. Let's write that as 3 to the 3rd power. Because why would you need this type problem? Okay, I've got memorized in my mind what the natural log of 20 or natural log of 3 is. And without a calculator, if I know what the natural log of 3 is, I can actually find out what the natural log of 27 is. I really don't, and I don't know why somebody would, but that's just my for instance. You're able to go from natural log of 3 to the natural log of 27. So I know that 27 is 3 to the 3rd power. I also know my 3rd rule of log says if I have an exponent, I can simply move it out front. So if I know what the natural log of 3 is, I can simply multiply the natural log of 3 by 3, and this is the same thing as this. So the natural log of 27 is simply 3 times the natural log of 3. The natural log of 9 would be 2 times the natural log of 3. The natural log of 81 would be 4 times the natural log of 3, and so on and so forth. Let's try another one of those. Oh, maybe not. The inverse rules, and I call these White House rules. Why? Because my college professor called them White House rules. Why did he call them White House rules? I don't know. I didn't understand it. But it got to me to calling these White House rules, so that's what I'm going to name them. The book calls them inverse rules. And this is your 4th rule of logs. And here it goes. The log base 3 of 3 to the x power. Actually, let's do 3 to the 4th power. Bless you. It's something about paint on the White House being white, and it's plain, and it's simple, and it's easy. I don't know. It just, again, it didn't make sense. If you ever have a logarithm to where the base and the argument are the same, this will always simplify down to whatever the exponent is. Log base 3 of 3 to the 4th is 4. Log base 5 of 5 to the 2nd is 2. Log base 7 of 7 to the 4th is 4. Log base smiley face of smiley face to the 5th power is 5. Okay, when the base and the argument are the same thing, your answer is simply the exponent. That should make, honestly, this should make sense from what I just showed you. When a log has an exponent in the argument, that exponent can be moved down front. So this is 4 times, this is y, this is your reasoning. That's 4 times log base 3 of 3. Log base 3 of 3, 3 to what power is 3 would be 1. So that's simply 4 times 1 or 4. And that's always the case. When these are the same, it'll always turn into 1, and this can always be moved out front. So there's your first inverse rule. When your base and your argument are the same, your answer, it always cleans up to your exponent. Your second White House rule. 5 raised to the log base 5 of 7. It's kind of the same thing. Look, bases are the same. This always cleans up now to the argument. 6 raised to log base 6 of 5 is 5. 9 raised to log base 9 of 2 is 2. I will do the proof of this one as well. It's a little bit tougher. Let's do 7 raised to the log base 7 of 4. We know that's 4 from what I just showed you. But here's why it's 4. Change forms there. That's actually in exponential form. You've got something to a power equals something. Change that to logarithmic form. And then you're going to see why this is true. This would be log base 7 of x equals log base 7 of 4. If you change that from exponential form to logarithmic form, dump your logs. Log base 7 of x, log base 7 of 4, obviously x is 4. And it always works out like that. When you rewrite that, it'll be log base this of this equals this. So therefore, your unknown will always be whatever that argument is there. Here's an example. E raised to log base e. Notice the base of this exponential base and the logarithmic base is the same value. They're both e. So that'll always clean up into the argument, x squared. Done. E raised to log base e. You can kind of think of it as this just cancels and leaves you with that hanging in the air, but we're going to write this as an answer. Your bases are the same. Log base 7 of 7 to a power. Your answer, that cleans up into the power, 2x minus 1. And again, you can think of that as moving that down front. Log base 7 of 7 is 1. Finish. Okay, putting it all together. Again, these are the problems I was talking about a while ago. We're going back, and these are the difficult ones. We want to somehow write log of 6 in terms of these two. Let's say that I give you a sheet of paper. That'd be a good way to do it on the test. Let's say that I gave you a sheet of paper, and I tell you what the log of 2 is equal to, and I tell you what the log of 3 is equal to. And I give you a basic 4-function calculator, and I say, okay, find the log of 6. You don't have a log button on your calculator, but you have this basic 4-function calculator. Tell you what, I'll do that. So here we go. Say that I gave you a basic 4-function calculator, does not have a log button, and I ask you what is the log of 6. Somehow use the log of 2 and the log of 3, which I have given you up here, to find the log of 6. First rule. I can rewrite the log of 6 as what? 6 is the same thing as 2 times 3. So then shall take this. Since 6 is 2 times 3, how could I rewrite from my product rule the log of 2 times 3? That'd be the log of, perfect. So how do I find the log of 6? I add this number plus this number. And I believe I would get approximately 0.778. So the log of 6 should be 0.778. It's the log of 2 plus the log of 3. That's it. Okay. We're going to work a few of these. They're like little puzzles. It's how do I get from there to 2's and 3's? Have the log of 16/3. And just knowing the log of 2 and the log of 3, you can find tons of different logs by using now basic arithmetic. The log of 16/3, Savannah quotient rule. I have a log of two things being divided. I can rewrite this as the log of, careful, 6. Okay, not divided by, but good. Perfect, good job. So that's a log of 16 minus log of 3. So I'm good with log 3, because I know what log 3 is, but I have no idea what log 16 is. So we've got to somehow now transform that 16 into either a 2 or a 3. Any ideas on how to do that? I'll give you a second to think on it, too. 16 is 2 times 8, like you said, or 2 times 2 times 2 times 2. 2 times, there's 4 of them there. So we now have log of 2 to the 4th power minus log of 3. Third rule of logs, I like this problem because you have to use all your rules except for the product rule. Third rule of logs says if you have a log of something to a power, that power can be moved out front. So that would be 4 times log of 2 minus log of 3. I know what the log of 2 is. I know what the log of 3 is. So I could actually plug those two values in. That would be 4 times 0.301 minus 0.477, which we don't have to do that because the problem actually just said rewrite each expression in terms of log 2 and log 3. I just put those two up there just to show you kind of why you're going in that direction. If I gave you this and this, could you find the log of 16/3? Okay, let's do another one. Log of 1/3 we've already done. That's the log of 3 to the negative 1, which is negative log 3, which log of 3 was 0.477, so that would actually be negative 0.477. It's the negative, excuse me, I didn't move it down front, did I? It's the negative of log 3. So the log of 1/3 would be that. Rewrite natural log of 45s in terms of natural log of 3 and natural log of 5. Colby, what would you do to start? 45 can be written as, give me something 45 breaks into. What multipliers give you 45? There you go. 9 times 5. So I took care of my natural log 5, but I don't have 3. I have 9. But we know that 9 is 3 times 3. So if you want to, you could write this as 3 times 3 times 5 and split it into the 3 separate ones. Or I'd really rather you see you write it as 3 squared times 5. That's 45. Product rule says split it into the natural log of 3 squared plus the natural log of 5. The exponent rule says to bring the 2 out front, so that's 2 times natural log of 3 plus the natural log of 5. So now you have it in terms of natural log of 3 and natural log of 5 in terms of, instead of in terms of 45. I think this is the last one of these before equations. No, goodness, we got a few more. We're really working on your ability to do these rules. Now in this one, we're asked to just split it into several separate. And there's a lot of this stuff on your test, this type stuff. So we have a natural log of 2 things being divided. Okay, first step, what I would do, quotient rule says the natural log of this divided by this would be the natural log of 3x squared minus the natural log of yz. Now something you do have to keep in mind here is that yz, the whole yz is on bottom. And if you don't do this correctly, you're going to end up with part of that yz on top. Here's what I mean. Now you've got 2 separate problems that you could split by using product rule. Natural log of 3x squared would be the natural log of 3 plus the natural log of x squared. I would actually put that whole thing in parentheses because that was the top part of your logarithm problem up here. Minus the natural log of y, again, these are being multiplied together, plus the natural log of z. The way I wrote it is incorrect. That's what I was trying to say. You've got to be cautious on how you write these. The reason it's incorrect is this whole yz was on the bottom of that fraction. The way that I wrote it, could I not take this plus natural log of z and move it out front here? That makes sense. So really, since I wrote it like that, I kind of put that z on top of the fraction. Be cautious when you're doing this because you really need to do this. It's minus that whole thing. The whole thing is on bottom, so you need parentheses there. So you have this stuff divided by this stuff. There's only one other step. I can move the 2 down front, so you actually just used all 3 rules. You have the natural log of 3 plus 2 times the natural log of x. Now, you can distribute this if you don't want parentheses. These parentheses are not necessary. The only time you need parentheses is if there's numbers out front, if there's a negative out front, if there's powers or exponents. These parentheses are not needed. These parentheses are needed because you have a negative. But if you would like to, you can distribute that negative. And you could write that as minus the natural log of y minus the natural log of z with no parentheses. Then it works out. This one's ugly. Terrible. Have log base 3 of ugly stuff. Just the only way to work these problems is one step at a time. Same way as when we were doing rules of exponents and you were given nasty looking stuff. And if you tried to look at the picture as a whole, it was really confusing looking. But if you take it one step at a time, because here's all you got to think. If you've got fraction bar, that's your quotient rule. So all of a sudden now you have log base 3 of top stuff minus log base 3 of bottom stuff. Looks a little bit better. Next up, you have log of stuff to a power Powers can be moved down front. So that's 2 times log base 3 of x minus 1. Same thing here, you have log base 3 of stuff to a power. That power can also be moved down front. Minus 3 halves log base 3 of z. Caution. A lot of you are going to want to take this x minus 1 and say, oh, subtraction, that's related to division. You're going to want to write that as log base 3 of x divided by log base 3 of 1. That's wrong. Okay? The rule is actually backwards. It's when you have the log of things being divided, you can split it into the difference of logs. The 2 logs being subtracted. This is not 2 logs being subtracted. Okay? There is absolutely no rule for when you have the log of 2 things being subtracted. That's as far as you can go with that. So, since we've dug the hole, let's fill it back in and do the exact same things the other direction. The natural log plus the natural log minus 3 times the natural log. Let's take those same rules, work them backwards. Allie, what can I do with this 3? Since it's being multiplied times this natural log, I can put it where? Good. So you have now minus the natural log of x to the 3rd. 3 moves up top. Brianna? You have a log plus log. Rewrite that for me. The natural log of, what am I going to do with x minus 1 and 3? Multiply them, so you have 3x minus 3. Everybody good there? Just combine it back together. Last problem, we tore it apart. Now let's put it back together. Caleb, what do you have when you have a log minus a log? That'd be the natural log of putting the pieces back together. Good job. Okay, the next one, we'll fly through this. Things being multiplied times log, I can rewrite that as the log of y to the 1/2 power minus the log of z to the 1/3 power. A log minus a log, I can write as the log of y to the 1/2 divided by z to the 1/3. Or if you don't like exponential, or if you don't like rational exponent, log of y to the 1/2, that can be written as a square root of y over the cube root of z. Again, that's simply your logarithm rules the other direction. Change of base formula we've already done. Just a reminder, the change of base formula simply says this. If you have a log of some base rate of, let's say, 7, log base 3 of 7, you can rewrite that with any base. Now, we use base 10 and base e. Let me say it again. You can rewrite this thing to any base. It doesn't matter. Log base 3 of 7 can be written as log base 10 of 7 divided by log base 10 of 3. You can rewrite this as log base e of 7 divided by log base e of 3. And for some reason, if you want to, you could rewrite this as log base 5 of 7 divided by log base 5 of 3. The change of base formula gives you a formula to where you can change a logarithm from base 3, as in this case, to any base you want to. Again, I don't know why you would want to change it to a base other than 10 or e. And the only reason you want to change it to 10s or e's, you can type those into your calculators. The change of base formula, again, simply gives you a way of plugging this into a calculator. And we've done enough of those. Let's skip on. Let's work a word problem. $2,500 is invested, and notice I've got your 2 interest formulas down here, compounded daily. Elizabeth, since it's daily and not continuous, will I use formula A or will I use formula B? A. If it's compounded daily, monthly, weekly, quarterly, semi-annually, annually, again, you'll use that formula A. If it's compounded continuously, you use the A-PERT. So we got this formula. Let me just blow it up so I don't have to rewrite it. Clear. Where you at? You have the principal, $2,500 is invested at 6%, compounded daily, 365 times a year. How long We're looking for T here. How long would it take the investment to double? You know what, guys? Really, that's not important. And I'll show you in a second. This formula actually would tell you, and I think, and Miss Robbins is doing it in her class right now. It's the rule of, what is the name of that? Rule of sevens or something like that. You can use for this type of problem, if I'm not mistaken. But let's go over this. How long would it take for the investment to double? So we've got a principal of $2,500, and what do we want our A to be? If we invest $2,500, if we want it to double, then $5,000. I'll show you in a second why that really doesn't matter. 1 plus the rate is 6%, compounded daily, right? 365 times a year, raised to 365 T power, because we're looking for T. Now, again, why does that 2,500 and 5,000 not matter? First step, well, before we do this, let's clean this up. So in my calculator, I'll show you how I would type this in. Come on. I'm going to do 0.06 divided by 365. 365. And I'm going to add 1 to that. And I get 1.000. Don't round that. Please do not round that, because if you round that to 1.0, it's going to throw your entire problem off. Okay, that needs to be exact. Right now, it is exact. This is not the last number. It's irrational. It keeps going forever. But even though your calculator stores that, if you do the answer raised to a power or something like that, it uses the exact answer, not that answer. So that's what I get here. But the cleanup, though, what can I do with this 2,500 and what will I do with it? I'm going to move it over here. This is being multiplied. 2,500 is being multiplied by this step. So to move it over here, I'm going to divide by 2,500. 5,000 divided by 2,500 will be 2. Now, why did I say that really doesn't matter? We wanted our investment to double. That value that I have there, 2, will always be 2 regardless of the numbers you plug in. If you want 3,000 to go to 6,000, if you want 4,000 to go to 8,000, if you want 5,000 to go to 10,000, or 1 million to go to 2 million, that always is 2 when you divide it. All right, you want it to double. So this formula doesn't just work for 2,500. If you invest 1 million and you want to see how long it takes for it to go to 2 million, it'll be the exact same answer. So 2 equals, I'm going to put stuff to the 365 T power. And the reason I put stuff is I don't want you to put that 1.0 or 1.00. It's that whole decimal is what I'm wanting you to use here. Now to solve that, to try to get T by, there's nothing else I can divide by, there's nothing else I can move over. So all you can do now is change forms. Log base stuff, right, of 2 equals 365 T. Now, how do you type this into your calculator? That's your change of base formula. That's log 2 divided by log stuff. If you'd like to, instead of stuff, now have I showed you how to store into these calculators? Have we done that? Watch this. You have an STO button, if I haven't already showed this to you. Since I want to use the exact answer here because it's so precise, it's so necessary that you have as many decimals as possible. If you hit STO, that takes this answer and it stores it into wherever you want to. You can do alpha, we'll do alpha A, hit enter. So now every time I want to use that number, it's in A. So what I've got to do, I've got log base stuff, or in this case it's A now. I've got log of 2, that's how you type it in, divided by log of stuff equals 365T. So bring my calculator back up, and I have log 2, wherever my log button is, log 2, close parentheses, divided by log of stuff, which I stored in A here. So every time I want to use it, just hit A, enter. I get 4,216. I'm not done yet. This stuff is equal to 4,216. I have one last step, Jordan. What do I now have to do to get t by itself? By enter. 11.55 years. So it would take 11.6 years. It would take 11.6 years for 2,500 to grow to the 5,000 that I'm looking for. Let's do one more of those, and then I will show you one other thing I'm done. From what annual percentage rate? Okay, now they're asking for the R. And just a reminder, when you're dealing with rates, before you can plug a rate into a problem, you have to change it to decimal form. And when you get an answer out, you're going to get the decimal form as an answer. You have to change it back to percent form. So compounded monthly, so we're using this formula again. We want 1,000 to grow to 3,500. So 3,500 equals 1,000. That's the A and the P. Times 1 plus R over N. Trevor, what's my N on this one? Monthly, so N would be number of times each year. If it's monthly, that would be 12 times a year. There we go. Raised to the NT power, which would be 12 times 20 years. Folks, this is not a logarithm problem. Does everybody understand why this is not a logarithm problem? Look where your variable's at. It's not in the exponent. The only time you need logarithms to solve these problems is when variables are in the exponent. That's the reason I worked this one, just to show you, just because you have this problem where you're dealing with interest rates does not necessarily mean it will be a logarithm problem. But this is actually a review problem. 1,000, let's move it over just like we did on the last one. When you divide this by 1,000, move it over 3 times, you get 3.5 equals 1 plus R over 12 to the 240th power. This is not a logarithm problem. But it is a type problem that we worked either last chapter or the chapter before. We have stuff raised to the 240th power. How do I get rid of the 240th power? How do I move that 240 over here? You raise the other side to the what power? One over 240th power, which is the same thing as taking the 240th root. So in essence, you're looking for what number can I multiply times itself 240 times to give me 3.5. I assume that's going to be a rather small number. How do I type that into my calculator? There's not a 240th root button on here. Now, some calculators do have this button, the xth root. If you would like to use that button, that's fine. It'd be the 240th root. But here's how I do it. I simply do 3.5. And if I want to raise that, or if I want to find the 240th root, I simply raise that to the 1 over 240th power. That's 3.5 to the 1 over 240 power. Enter. You get 1.005. Very small number. If you multiply 1.005 times itself 240 times, you end up with 3.5. You're not done. You got rid of that. You now have somewhere around 1.005 equals 1 plus R over 12. You're now simply solving that little linear equation. And we can use our calculator to do it. Next thing I would do is take this 1 and subtract it off. So I'm simply going to take this answer and do minus 1. Enter. Now I have 0.005. My last step, now that I've got rid of my 1, divided by 12, move it over by doing times 12. Times 12, enter. 0.063. So that's the interest rate you're going to need. Move it over twice. This is interest rate, so move it over twice. You have 6.3% interest. 6.2% would not reach it. Does everybody understand that? 6.2% is not going to grow 1,000 to 3,500. It will come a little shy. because you need a little bit over 6.2. So in order to ensure that it makes it at least 6.28, or 6.3 would actually give you a little bit more than 3,500, but there you go. The other thing I wanted to talk about, and I promise this is it, is go back to this 11.6 years, and we're actually, next chapter we begin trigonometry, and what I'm about to show you is related to trigonometry. And just while I have this up here, just real quick, 11.6 years doesn't mean that much to me. Let me show you a trick that you can use, because I want to know the exact time in years, months, minutes, seconds. I want to know the exact time when I reach what I'm supposed to be reaching. So 0.6 years, I don't know how many months that is. Okay? And we're going to be doing this next chapter. Like I said, I'm kind of getting ahead of myself, but at the same time, I'm doing something with trigonometry. I'm relating it to something you know, like years. 0.6 of a year. What is 0.6 years? How many months is that? How do you find that out? Well, it's 0.6, that's 6/10 of a year, and I know that there's 12 months in 1 year. So what I can do is, in order to turn that into months, that's 0.6 of a full year. 0.6 of 12 months. If you type that in, that gives you 7.2 months. The word of in math means times. So 0.6 of the full year, that'd be 7.2 months. So now I've got 11 full years. I've got 7 full months. But does everybody understand it's a little bit over 7 months? So that other 0.2, let's say that on average we know that there's 30, let's say on average 30 days in a month. And if I wanted to take that 0.2 and I wanted to translate it into days, well, that's not a full 30 days, that's 0.2 of the 30 days. And if you multiply that out, that gives you 6. So 11 years, 6 months, and 6 days. That is your translation of 11.6 years in days, years, months, days. And you could do that, you could go on further. If you had it more exact instead of 0.6, you could bring it down to the minute of when it's going to change.